Welcome to another edition of the ECE Launch Distinguished Lecture Series. I just want to remind you that this is probably the last lecture for the spring, and then we'll restart again in the fall. And there is a culmination event, November 5th and 6th. So put that in your calendar. So we'll announce that probably in the next few months. So we'll have a day-long event on November 6th and probably a lecture on the evening of November 5th. Okay? So without further ado, I'll invite Bill Sanders to say a few words.
I also won't say much because we want to give all the time to our speaker today. But I'd just like to remind you all of the purpose of this launch series. We have moved into this incredible new building, and we are using this as a launch pad to think about the vision for electrical and computer engineering for the next 30 to 50 years. And this is an example of one of very high-level speakers that we are able and very fortunate to be able to bring to help us in that dialogue. And we look forward to all of you in the audience who came, and thank you for coming on the first day of finals. All of you are our future. So we really look forward to working with you and inspiring you to be the change for the future. So I'd now like to introduce Bruce Hayek, and Bruce Hayek will introduce our speaker.
Thank you, Bill. Did I turn this?
It's on.
Hello? Yeah, thank you. It's my pleasure and honor to introduce Arvind, the speaker today. Arvind got his bachelor's degree at the IIT Kanpur and MS and PhD here in ECE, Illinois. And he was a bright student and a very cheerful disposition. I was just looking for predictors for success. I think it was his pleasant personality and ability to go after any problem, undaunted and always cheerful. After that, he went straight to IBM Research, where he started working on RFID tags and other things with a small group. I visited once, he had like 4 or 5 people there, but then his groups just got bigger and bigger. And then after 11 years, he went over to the business side of IBM, sometimes called the dark side. And he became a vice president of Tivoli, and it's a software business owned by IBM. And groups just kept getting bigger and bigger, and to thousands of people and budgets in billions of dollars, real life decisions, hard decisions. And then just a few months ago, he came back full circle to IBM Research, where I think he's in an excellent position to sort of understand IBM software business, especially security and all kinds of things related to that. To put that together to make IBM a leader going forward in research. And without further ado, I'd like to have you help me welcome Arvind to the podium.
Thank you, Bruce. So, look, let me start by saying that if I look back at my years at Illinois, I'll have to say it was the most incredible experience of my life so far. The years here, the learning here, the interactions here with the faculty, the camaraderie with the other grad students and the faculty, all of it are a contribution to what I have achieved. I'll also tell you that you can take learnings that you take and you think you'll never apply them, and you can apply them in fields that are far, far afield. You gotta keep your mind open to it. I mean, many of you probably study linear algebra, and some of you probably wonder, why the hell would I ever use that again? And if I tell you that you can apply linear algebra to understanding the fundamentals of any business, even if you know nothing about the technology, you'll kind of look at me. Because if you look at anything, what is linear algebra and vectors about? It's about trying to compose something down to its basics. So you look at a complex business, and IBM is certainly a complex business. We're not a small business, we're not a tiny business. We're in 195 countries across, let's call it dozens to be kind. It's probably thousands of major products with disparate sales forces, with disparate engineering teams, and you want to decompose something to make some sense out of it. What are you going to apply? Right? You're going to go back to those concepts, certainly, But more than that, you can even begin to apply those math techniques. So just one small example, right? Always learn something and keep in mind, how could I apply it going down the road? Because you won't be able to predict where. And that really brings together to me many, many things. For today, what I really am going to talk about a little bit, I think that information technologies had a fantastic run, right? You can say whether it's 50 or 60 years, people talk about the communications and IC revolutions kind of drove it. Those started clearly in the 50s and have driven it forward, so 60 odd years. But I think that we are at the crux of something today. As I walked around campus today and yesterday, some people talk about Moore's law, and I'm really going to focus on kind of how do we make advances further given at some ends that we see coming. So quick context on IBM Research, because I certainly hope that we'll be able to recruit some of you towards those facilities. We have 12 locations around the globe. We are on 6 continents, and it can be an amazing experience to people in certainly geography. But the geography is important not just because, for example, it's in Kenya, or it's in India, or it's in China, or it's in Australia. The problems that you tackle are far, far different. I mean, few people here would worry about how do you go optimize large-scale strip mining, natural resources in Australia or Brazil. That's the number one topic. If you're in the Middle East or Brazil, you worry about extracting oil from deep sea wells. And by the way, that's not only a petroleum engineering topic. The hardest problem to solve there is a computational problem on how do you actually discern signal out of the very noisy seismic signals that you get back. The kind of problems we work on are really large scale. You can move the needle forward on the science, but you can also begin to see almost immediately what the application of it is. And that's our prime reason for having locations around the globe. We take a lot of pride in past history. We are not at the scale of the College of Engineering at the University of Illinois, but we do have 6 Nobel Prizes and 6 Turing Award winners, and I think 10 medals of science from the US Congress and the President.
Some of those categories you have a speed.
So when you look at that, we take pride that yes, we are certainly a commercial entity. I mean, I make no apologies for the fact that we are a shareholder-driven company in a capitalist economy. That said, you can, and it's a fine line, you can also progress what you do for society. You can also progress what you do in moving the science. You can also do progress in improving things that are feasible that many people believe are not. You can actually achieve all of those, and I think that those accomplishments are sort of evidence of that. So it gives evidence to the quality of the people, to the eminence of the people, as much as it does to the institution that helps them thrive. So moving on from there, I mean, look, data is growing. We can argue whether it's 44 zettabytes, then the other side will say it's going to be 100 zettabytes. I mean, somebody else will say, no, it's 20. I mean, it doesn't really matter. If it's going to grow another, not by 40%, but by 40x over a half decade, driven by all the factors that all of you understand, right? 800, what is it today? I think 800 million smartphones, 3 or 4 billion mobile devices, sensors everywhere. People talk about 30 billion odd sensors. That means it's like 5 for every human. They're soon going to go to 300. You instrument railroads, rail tracks, light bulbs, all of these things. You get a lot of data. What are you going to do with this data is a big, big question. You can say, well, I have some great ideas. Let me go apply all the computing techniques, the algorithmic techniques, the deep learning techniques, the AI techniques. Well, I'll say, but there's a big but. So kind of what's the big but? I mean, other than the advantages which we talked about, microprocessor clock rates have kind of stalled. I think, yeah, it's possible to prove in a lab that you can have a faster transistor. People have 10 gig transistors and all that, but they're not really manufacturable. If you look at what's manufacturable, it's being driven down into the 1 to 2 gig range mostly, and that's not going to move. I'll sort of make a bold claim. For the bulk, it's not going to move much beyond that because of power limitations, because you can't draw out much more power from these things. So if you can't draw out more power, you can say, hey, what about storage? Because I got all this data, but storage performance is also losing ground. If you look at the shape of that curve, it's beginning to flatten out. And this is the I/O. Sure, I can get a lot of density. Maybe I can put 8 terabytes on a drive. By the way, when they get to about 20, you're going to get to be solving error correction problems that are going to cause you slowdowns in getting out sequential data. Right? That's pretty well known at this point because you're reaching the limits of what at least the materials known today can go get done. So if you say, all right, microprocessor clock rates have stalled, what I can get out of a disk has stalled, so if I put a lot more data in there, I'm still processing it at the same rate as before. I'm not processing it any faster. So you can say, well, let me build a wide system, right? That's the other answer. So when you go to a wide system, well, the data graph was exponential, but your network graph is linear. So you've got to rethink fundamentally, I believe, what is going to be the computer architecture, what is going to be the design point that is going to say, I got all this data, I know there's advantages in it, whether for health, oil, telecom, you can go on, education, etc., all those things. The current architectures are not going to get us there because the cost of doing them on the current architectures will not be sustainable. Right? So if you say you want to get beyond that, what is it that you're going to go get done? So you got to say, how am I going to create a data-centric system? And I am no doubt going to get some hate mail or flame mail, I'll say, from some purists, but I'll say, look, we're living on the John von Neumann architecture, right? Which said you have storage, you move from storage to compute, you do some operation, you put it back into storage. Okay, whether it's DRAM, whether it's storage, that's kind of the architecture we've been living with. And then we extend it with things like vector computing. You extend it by saying, okay, let me wrap these things together. And the fact that distributed or parallel doesn't quite scale was observed not by us, but 30 or 40 years ago, whether you want to call it Amdahl's law or something else, but the cost of distribution at some point overweighs what you get. So you've got to rethink this. Maybe you want to, in very simple terms, move the compute to the data. So you say exactly where the data lives, you go do a lot more compute. And there are many, many architectures that can go do it. I don't have a favorite one. But it is going to fundamentally redesign how you do algorithms, how you do systems, etc. We ran some simple examples. I mean, we ran some examples that if you take this idea and apply it to sorting, which is probably, I'll say, the most well-studied algorithm ever. I mean, for those of you who ever took a class on algorithms and you bother to go read Knuth, you can go through pretty much everything. So from a theory side, there's not a lot more. So you ask yourself a question. Okay, so I know the 30 different variants I can do. If I go apply that to a modern machine architecture, and you now compare the result you get with the best commercial library available, whether for parallel or for single computers, what kind of advantages can you get? You can begin to get advantages of 20 to 40 times. So those are incredible. And by the way, they scale with the size of system. So there is a whole topic around how can you optimize things, taking modern machine architecture into account. Now, I'll admit we get a little bit of freedom because we're not only using commercial computers. We can say things like, hey, I want to put a bit more logic down on my memory chip. Hey, I want to do some more simple blocks which are sort of reusable and not reprogrammable down in those things. But as you begin to do that, you get huge advantages. And the ability to go do that is, I think, going to transform how we think of systems. So when you think about accelerators, it's not just about doing an accelerator for encryption or compression or maybe an FFT. You've got to really open up your mind to say, let's rethink through, because it's so baked in, the von Neumann architecture where you have a CPU, you have DRAM, you have storage, and then you move things back and forth. But it's not fundamental. I mean, nobody wrote an immutable law of physics to say that's the only way to do things. And this ability to distribute compute back to the data, I think, is going to drive a tremendous amount of these things. And clearly, when you think about the amount of memory versus the speed of memory versus the latency, There's all kinds of advantages you can have. And we've kind of lived with this hierarchy, right? And those of you who are circuit people who worry about cache designs, I mean, you spend lots of logic in worrying about what populates the cache, what do you throw out, what do you bring closer, because like it or not, you get closer, you get a magnitude advantage in speed and latency. Unfortunately, the size is often 2, 3, 4 orders of magnitude smaller. But if you can move that compute back out, you now begin to get advantages fundamentally in computer architecture. So really, as you begin to think through what kind of problems this thing, so we did a little bit of modeling to say, if I can do a little bit of logic closer to the memory, so you say, look, you're not going to go redo in 1 or 2 or 3 years entire operating systems, entire ways to manage petabytes and exabytes of data, so I'm going to use what I got to manage all that. But if I got to operate, for example, I'll pick my oil field example, it could be a couple of terabytes of data you get to operate on. What's the advantage of doing that? If you can, with more precision, understand where oil is in the deep sea, you can make a single well which costs $300 million. Today, the hit rate is about 20%. So you say it costs them $1.5 billion to get a single effective well. If you can get with more precision where the oil may be, you look at me and say, well, couldn't you do that with what they got? Deep sea oil is under a bed of salt typically. And when you put the seismic waves through the salt, they tend to refract in ways that make it really, really hard. So you got to improve the granularity of your precision of the compute down from tens of meters down to single meters because of the error going further once you get 5,000 meters away. And so the ability to do that makes these problems more feasible, and kind of the techniques that I described can get you a 100x advantage in time. Because that geologist, if you tell him it's going to take a year to run your problem, looks at you and says, go away. I mean, they don't have a year because they need to run it hundreds of times to begin to compute across fields. You can have plenty of other examples. People who make bids on telecom spectrum, people who are worrying about genomic samples, people who worry about what's called the microbiome, right, or the collection of all the bodies in your gut or elsewhere, or in cancer. These techniques on 3D imaging and being able to apply, I'll call it classic math. I mean, in the end, you're doing partial differential equations to go solve a problem. That's what is solved here. It's solvable because it is a nearest neighbor problem, which tends to be a very repeatable pattern. So it is simple circuitry to put back on. And then there's a whole class of other issues that open up, right? How do I make it less power intensive? How do I begin to, what kind of compiler, what kind of programming model? It opens up, I think, a rich set of areas you can go after. Then you say, well, is there only one thing that I want to optimize or many? And then you say, well, what kind of thing do I want to do? If my computation, does it have spatial locality or is it sparse? Am I worrying about floating point or am I worrying about integer? Am I worrying about getting to visualization? All of these will begin to determine what kind of system you're going to go build in the end. Because if you go talk to a medical doctor, they want to actually look at the image and for you to point out where you think there might be an artifact or something for them to worry about. You worry about an oil field guy, he wants to know which is the best location for a well. He may or may not be that interested in the visualization aspect. You talk about pollution, because you can actually use these same techniques to go predict how much pollution might be. And here it's probably less of an issue if I think of central Illinois. But in most of the emerging markets, there are still a lot of coal-fired plants, and I'll call them polluting things, that they can actually shut down if it reaches a level where it's harmful to your health. And you can begin to apply all of these techniques. So some require visualization, some have locality of data, some do not, some require randomness, some require other techniques, and you can begin to go optimize the system against many of those different dimensions. And for the sort of the physicists and those who's doing, I'll call it high energy particle physics, this is like, it opens up a whole new avenue of possible research for them. So really, what I didn't sort of give you much of what IBM is doing here, but if you look at it, what we're after, we build these systems called Blue Gene, which I'd say was really the idea of lots of little processors. So it's great for the nearest neighbor problem back in the late 2000s. We are really after building the first data-centric system, and we will deliver, I'll call it the first instance, it's hard to ever say it'll be the ultimate instance, of it to the Oak Ridge National Lab and to Lawrence Livermore about 2 years from now. Those systems for the HPC geeks in the room right now are at about 150 petaflops, single instance with about 100 plus petabytes of storage and a few terabytes of main memory. And they do allow you to bring the compute to the data. And we really are after building exascale systems that I think truly allow you to solve all these problems. Now, sort of, when you look at these systems and you begin to say, hey, what could I do around them? And I'm going to pick an example drawn from energy. So we talked about oil. Health, I think, is in all your minds given all that's going on campus. So if you look at energy, 143 gigawatts of renewable capacity was added, right, 2 years ago. By the way, 141 gigawatts is all we got using fossil fuels, right, which is what I'll call it putting moral judgments aside. Many governments certainly want to reduce the dependency on fossil fuels. You can make it economics as opposed to any other aspect go drive that, because importing oil or importing coal is going to cost you. And you know that you're going to get 150 petabytes of smart meter data, and that's just a US number. We lose $14 billion in productivity due to storms because they knock lines out, and communities as well as industries cannot operate. And estimated 20% globally of electric power is stolen, meaning, well, it's consumed, but no one pays for it. This is not counting losses due to heat and other things which also happen. But the 20% is pretty high. In any other industry, 20% would get you out of business. And so you begin to look at the data, right? And if you look at what has been analyzed forever, is that bottom part, which is the customer consumption. And now you begin to say, well, what else could I use? Well, asset health, because that conveys how efficient you can be in terms of the age of the infrastructure, what can different pieces do. People talk about instrumenting the grid. That's 10 times as much. If you get into trying to get into leveraging weather to control supply and demand, because you can, if you're going to predict there'll be a heat spell there, you can design and control your grid to flow more energy a certain place, as opposed to, for example, Alabama saying, hey, I need a lot more power plants locally, or California getting throttled and raising the spot price, I think, to what was it, over $1 per kilowatt hour, which was about 4 or 5 years ago. So these are real issues that go happen, and you have to go look at these things. And if you look at now getting down to instrumenting, down to individual large consumers only, there's another 200 petabytes that you can go take. So when you look at the amount of data, look, the state of the world is you've tackled that bottom 3%. That's kind of where we all are. All the remaining, I think, is yet to be tackled. But if you try to do it using traditional techniques, the cost, complexity, and labor, all three of doing it, stops people. Because the chance that your local utility wants to stand up a supercomputer and hire a couple of hundred PhDs to operate it, and then another 300-400 programmers to go write every analytic that may or may not result in this thing, is low. So it's got to become a lot more consumable as a collection, is kind of the main message that I want to leave you with. A second thing, since you're talking about the future, look, lots more stuff is going to happen at the edge. Whether you want to talk about sensors, whether you want to talk about instrumentation, what's happening at the edge is fundamentally going to change how we look at stuff, right? Then you say, but it also gets lost. The value of some of this data gets lost, and whether it's in milliseconds or seconds. I mean, if somebody is having an emergency medical condition, that data is useful for a few minutes. After that, your action may not have much impact, right? You look at the data that is used out of the data created. I think I'll say 90% of data is lost or not used. Is probably a very kind number. If you ask my true opinion, I'll say 99%. People just ignore it. They collect it and they don't know what to do with it. It just goes down a black hole, right? The computing and storage capacity of smartphones, by the way, not the total number, the storage capacity of smartphone exceeds that of all computers somewhere in the next 2 years, right? And I don't think people think of it as devices that hold data and effectively are part of some conceptual computing grid in some sense, as opposed to the other devices. Automotive, right? You want to instrument your car, you're going to spit out 1 gigabyte per day of data. And that is what is scaring these guys, right? You guys, I'm sure you all hear that Apple may or may not enter the automotive business. I bet you they're not designing a Tesla competitor. I'll bet on that, which is what the news says. But could they be designing electronics that you talk about instrumentation and making the car more user-friendly? Absolutely. You talk about mobile sensor types. I mean, the Apple Watch, which just got released, has more sensors than they can turn on. Or they turn them off because, one, they don't know what to do with some of them, and two, the power is still an issue. You don't really want to charge your watch every hour. Cameras, if I remember correctly, the City of London has 55,000 cameras or something like that. They do record them, but there isn't any real-time analytics done on most of them, except for a few rare ones on which there are some agencies that do some stuff. But most of those are around border protection, not around crime. So I think that if you look at this here, I think brain-inspired systems, because which is one of the best instruments that looks at edge data? Your brain, right? We talk about 5 senses. Some people will claim 6, but kind of I'll stick to 5. Your brain processes that edge data. If you look at trying to recognize humans or trying to recognize moving vehicles, what's the current estimate of a computer that can do it using standard technology versus the brain? So the brain uses between 20 and 50 watts. Doctors tell me, I'm not going to do the measurement myself, that if the brain reaches 70 watts of consumption, it begins to superheat to the point where it will actually no longer function ever again. You can't get the heat out. So if you're at more than 70 watts for a few minutes, you're dead.
And how variable is the wattage consumption depending on what the human is doing?
Quite a bit. So 20 to 50 is the range that it operates in. And it varies dramatically in there, in that 20 to 50. If you talk about today doing those tasks that we do so well, by the way, it is learned. I don't think babies kind of get born with those, with some of those things at least. It is around 6 orders of magnitude more. You're talking 5 to 50 megawatts. If you park a camera, let's say on top of whether it's Interstate 95 in my neck of the woods or I-10 that enters Los Angeles, the ability to do what the human brain can do, pick out all white trucks coming down an 8-lane freeway, is somewhere around 50 megawatts. So you're talking 6 orders of magnitude. So trying to solve these problems around edge, you're not going to do that. And then you begin to say, well, why is it 6 orders of magnitude? Is that kind of fundamental? Is it in the algorithms we do? And the answer, it's all of it, right? I mean, one observation, your brain is not a clocked circuit. It's not. It's asynchronous. And then for those of you who design those things, how much of your power in a chip is taken up by clocking? I mean, 70%? 80%? I mean, you think about just your DRAM thing, you're sort of switching it with every clock cycle, right? So you got to say, okay, so I got to say, the reason I'm calling it brain inspired is because you begin to look at, well, the 6 orders of magnitude. Maybe I can't get all 6. Could I get 2, 3, 4 orders of magnitude down by copying some of the ideas of what the brain does, and then begin? So you think about the brain, and you say, well, if I want to do this, then I got to connect all these neurons, and I want to simulate that, and that's 10 billion neurons. And I don't know how to connect 10 billion. Nobody's built a 10 billion by 10 billion switch, right? But the brain doesn't connect everything. It only connects some passages. By the way, you can observe that there are areas where there is rich connectivity. There's lots of areas of poor connectivity. And the connectivity actually aggregates into main trunks as you go along. So you take what neuroscientists are doing in all of the work around the brain project, and you begin to turn around and say, hey, can I do that? And what could I achieve? And I'll show you a little video as a demonstration of what is achievable here. So you look at this and you begin to say, hey, what's my error rate? So it turns out there is a scale. I mean, if you get to a certain scale of neurons, you can get to very acceptable error rates. Now, most engineers and computer scientists like error rates to be 0 because I'll have some of you throw rocks at me because we like deterministic computing. But humans are not deterministic. I mean, we all make errors in recognition. I'm sure many of you have said, well, I remember it as this, and you're 100% sure it was that. And all your friends, colleagues, maybe professors remember it as something else, right? Because we are not perfect. So the question is to get better than or equal to humans, not to get all the way down to certainty. So you say, okay, so scales of millions kind of get you there. And the scales of millions get you there, then you sort of say, well, what is the energy efficiency that I can go get? So you can say, hey, if I'm in software on a CPU, and whether you benchmark it, I'll say to the two CPUs that we bother about, one could be an Intel, the other could be a Power, you'd be, let's call it, it's at about 10 to the 5. You can begin to say, hey, I can use GPUs which get you down. By the way, it gets you a factor of 10 improvement. So not to be sneezed at, right? For these kinds of problems, not to be sneezed at. You could turn around and say, I want to do a lot more work. I don't want to just do some FFTs and some neural networks. I'm willing to write VHDL, and I'm willing to go program an FPGA. You get another 10x from that because you can begin to use lower power things, and you're not, typically, by the way, in any main processor today, you're using maybe 10% of the logic. The other 90% is just sitting there chewing power. So in an FPGA, you have the chance to go throw out the parts you don't want. So you get another 10x. It's not magic. You're doing a lot more work. And then this system that I'm describing can go get you another 100x from there. So you can get about 3 to 4 orders of magnitude down from standard CPUs. So kind of what was the insight and what was kind of the magic behind this? So one, the insight was, let's have an asynchronous system, completely asynchronous, no clocking. So you really got to go to firing neurons in hardware, not as software. And the moment you go to that, then you say, I need to be rich enough, which is why that insight of if I can get to 1 million or so that are fully connected, I can make a lot of progress. So you go put about 4 million neurons with a very rich connectivity on a single chip. And you can go do that because the scale today allows you to talk about 5, maybe 7 billion transistors on a single chip. That's kind of the manufacturing at reasonable economics today. So those will move some, but probably not a huge amount, as I showed in my first few charts. And then you say, I want to knit together the system to go from there. And to show you a video, this is a single board of that. This is on a tower at Stanford. The goal was recognize all moving objects. This system was 7 watts. We compared it to a 7,000 watt, which is about a 4 processor system, and that one missed 1 out of every 2 movements. So this video was used to win the DARPA competition on this topic last November. Okay, so when you go from there, so you kind of proven you can build it. So you've proven this idea of asynchronous neurons, etc. works. And so what we're after now is to try to build this into a much, much bigger system. So the 7 watts I'm talking about is a single chip board. By the way, you don't need that. Speech recognition requires a single chip. You do not need billions of neurons to get to speech recognition. For video, you do. We know that we can get to a rack which is on the order of a trillion, and it's a 4 kilowatt system. That is still not where you need to get to what the brain can compute. So we are still there. We know it's feasible, but we also have to at the same time solve the issues of what are you going to go program this thing with? You're not programming it with Go or C or Java. You got to fundamentally rethink how you're going to translate the algorithmic concept. It's not an algorithm anymore, into something which is about firing neurons, because the way this works is neurons fire. If you collect enough signal, then you're going to fire yourself, and so on. It's completely asynchronous, so you got to worry about all these things around convergence, which class of problems can it solve, etc. We are pretty comfortable it can solve neural net problems. We are pretty comfortable it can solve pattern recognition problems. We are pretty comfortable it can solve some class of deep learning problems. But having said that, the gap between there to implement it is quite a bit. I mean, for speech, for video, you've seen that we've gone ahead and now demonstrated systems. I think to me, this is the beginning of a class of systems like this. And I think it changes, again, the nature of what's going to be possible. Now, we talk about a bunch of examples, whether it's in healthcare, robotics, sports. You can go ahead and begin to then imagine where you can apply these technologies. I mean, when you think about your smartphone, battery is about 10, 12 hours, maybe a day. Why? Because you're keeping on a pretty power-hungry processor to do all the tasks. You don't need to. Could you turn it down by 1000x and do other things? Could world of autonomous cars. I'm not a fan of that, but that's only because I like to drive. So, but plenty of people would love autonomous cars, or maybe other form of autonomous vehicles. And all these techniques, I think, are going to come into play for what goes on there. And sort of the last point I'll make today is, I think the problem scope in all these cases exceeds our capacity to get these systems programmed. And that's not a new insight at the gross level. I mean, there are folks in this room who have worked on parallel computing systems for decades. And it's always been that you need some kind of model to go do these, because the average programmer cannot do it. I mean, I use the example that, in automobiles, if you ask the driver that you got to have in your hand a couple of 10, 30, 40, 50 cables, and that's how you drive your car. You juggle when you open and close which valve. You juggle how you control fuel. You juggle how much oxygen goes in. None of you can drive a car. But that's what we're asking the programmers to do. You worry about thread management. You worry about memory management. You worry about when you do I/O. It's not going to be possible to build these kinds of systems. And I'm not talking about the end user. I mean, hopefully they'll consume it. I mean, the programmer, even at the shop who puts the system out, you're not going to do that. I mean, I'd assert there's maybe a few thousands of people in the world who can do it. There certainly are not millions to solve these problems, right? And you say, well, is there a big opportunity for us to use this? Well, certainly. I mean, oncology or cancer treatment is a big one. And at least hearing even about some of the projects that are going on this campus, that's recognized. By the way, rare forms of cancer have a close to 50% misdiagnosis rate. Miss is that they miss it early, but it's found a year later. By the way, that makes your cost of solving it 10 times more. And for some doesn't mean rare. So some of these are common forms of cancer. How retailers can improve the customer experience. Cybercrime losses, so you can apply it to really, I mean, I know that's something that a lot of people here, including Bill and team, have been after for more than a dozen years. Can we get much more systematic about understanding how cybercrime, which is an aspect of security, happens? And most of this is people break through the perimeter. So I don't believe that there is a firm perimeter anymore. Okay, that's a.
You can mine all that smart meter data you talked
Right.
about earlier.
And do stuff to people's homes.
Yeah,
Right.
we're doing that.
So the second one, in terms of, so other than the first IBM this thing, so we did build a system called called Watson about 4 years ago. And the point about Watson is that it's actually a learning system. So once programmed, it doesn't really solve a class of problems. It has a methodology. It can ingest data. Once it ingests data, it can worry about what it forms as evidence or hypotheses from that data. So you see data curation is a long phase, but the computer does it, not humans. And then when you ask it questions, it gives you answers. So forget the actual Jeopardy machine for a moment. If you ask it a question now, right, the real machine underneath that, it'll tell you, here are my 7 hypotheses. Here is the evidence I have for each hypothesis, and this is my confidence in each of those hypotheses, right? Like you guys remember which US city had a big airport in World War II, and it said Toronto, which was obviously wrong, but it probably found some evidence in some articles that linked Toronto. But if you ask it, well, we have this kind of cancer for this kind of person in this kind of age group, and these are the other things we know about it, it can tell you by reading through 23 million articles that here were the 17 most effective protocols, and very few oncologists would have had that base of knowledge to go read the entire literature and then to say, and here is the evidence against why I'm saying this. So now as a physician, you can figure out whether that evidence is meaningful or not to that particular thing. Then you say, where else can I extend that original idea? So we talk about message resonance, right? And you can say, well, what do you mean by message resonance? So you can look at what people write, what people type, what people say, and you can compose things back that they're more likely to respond to than not. Of course, none of you have ever sent an email to somebody hoping for a response and not gotten one. So being able to communicate more effectively is again a place where actually computers can help, because all the work you do in first understanding all that language can now be applied back. Once you begin to understand message resonance, you can talk about personality insights in terms of how are people going to react to different kinds of approaches, not just in language, etc. So those are some that are going on. Genomic medicine is another one. I mean, I talked about the 23 million articles and so on, but really when you begin to look at doing personalized medicine, and you look at saying, well, okay, if I got 800 billion base pairs, how am I going to go about looking in the literature for what may suit that, right? Which is why this has been an approach, but not yet an answer. You got to begin to then say, okay, out of the known drugs, out of the known genomic, given this person, you want a machine to help you pass through the known literature, which is literature. It's in language. You have images, you have graphs, you have pictures, to sort of dig through that, to really pass through here. Go try these drugs, go try that. For example, if you say, I'm looking for something which may attack this protein, you can now use machines to say, well, based on what I can see, this 6th class of drugs may be able to help. These other 600 that are related actually don't. But that language and something often gets lost kind of in history, because people did discover that, but there is no way to go pass through all of the literature today. Final example, we're talking, and this is going to be through a melanoma example, is really applying these techniques not just to language, but to images. So you really take the approach to say, hey, how can I assist in effective skincare? And if you look at the skincare example, you can begin to look at melanoma images. So melanoma is one of these cancers that is actually very hard to diagnose early on. But if you do diagnose it early on, it's relatively more straightforward to go get fixed than if it's later, in which case it tends to really spread and is much, much harder to catch. And if you look at it, you can sort of same approach, whether you talked about the video, whether you don't want to program it. You want to tell it, hey, I'm going to give you a couple of thousand images and I'll tell you these have melanoma. Not how much, not how little, it's got melanoma. You give it a couple of thousand and say it doesn't have melanoma. And now you want to say, how good is the system at figuring out how good it is? And so once you get there, so that's why we're calling it supervised machine learning. So you teach it, these have, these don't. It's going to figure out from the image. So you're not giving it, here are artifacts in the image. You're just giving it a raw image. Let the machine go figure out what is and isn't. And you can do that to begin to get to a machine which can begin to say, hey, I'm pretty confident that these do not. I'm pretty confident these have. By the way, I'm unsure about these. And that, by the way, goes a long way towards helping solve these kind of problems. So whether it's telemedicine, whether it's in the office, whether it's in other places, these are all examples, I think, of where machine learning is going to go. And I'll sort of pause on this page. So natural dialogue and argument development is something that certainly, let's say, lawyers care about. Because could you read through, for example, if we ask you to form two sides of a hypothesis, pick anything you like, whether it's something that maybe a fourth of this room cares about, like pensions in Illinois, and what are the 2 points of view on that? Or or whether you worry about different cases in front of the Supreme Court, and you sort of say, can you crawl through the literature? In this case, there is a trove of literature, LexisNexis or Thomson's, you can take your pick. Can you form two arguments? And a challenge we put upon ourselves, I mean, we made a lot of progress because we can form now two hypotheses, and it is interactive to say, what are the points of view? Can you give me the evidence against them? And sort of if you do that, you've just short-circuited somebody's work probably by days of having to crawl through all of the literature and do that. The last time I tried it myself with our team, in this case a team in Israel is building this, in about 20 minutes, you could give it a topic and have it crawl through, and with a little bit of supervision, it says, I think these are the pro and con arguments. Typically you find that a couple of the pros are not really meaningful, a couple of the cons are not really meaningful. You prune it, it actually gets better because it says, whatever logic I used to derive those is incorrect, so it throws out things like that. And you can begin to construct something and actually spit out something that, of course, nobody at a university would ever use as a term paper or anything like that. But it can get pretty powerful. So I think the ability now, and it's, the computer is advanced, the computational linguistics is advanced, the natural language understanding is advanced. In context, all of these things have advanced, is I think really pushing the state of the art. So really when you think about this, I'll sort of wrap up and say, look, Moore's law, to put it simply, I think is going to stop advancing in the simple way it has been advancing. So new system architectures, I mean, the time is ripe now. There is no more time when there's going to be more resonance to new architectures than right now. There's going to be a lot more data, whether from the edge or from the rest of the world, that you can take advantage of to create incredible value, innovation, new companies, new insights. It's going to disrupt entire industries. Right? And if you look now, I'll call it both the last two topics, whether it's synapse topic or cognitive, they are biologically inspired. I mean, they're really trying to say, well, how come my brain does these things so much better than anything in the compute world? That doesn't mean to me it's two different worlds. It's about, okay, how do I bridge? I had a certain architecture, I wrote its course all the way. Now how can I take in these new concepts and do things and do them in a way that's a lot easier and that's a lot more approachable to the average? Because if it's not approachable, you're not going to be able to solve it. So thank you all for listening.
Thank you, Arvind. We have some time for questions.
If I look at history, it said our students used to calculate everything by hand and so on. Not you have calculators, and so we say, okay, you don't need to do this very well, and then you have a calculator. And then we have the spell checkers, and then they say, okay, you don't need to spell very well, you can just do spell check. If we can have something that can think and help you to think and so on, are we going to tell our students that you don't need to think very well? At that point, actually the real question is, what are we going to tell them at that point?
So actually, I don't believe that this teaches you how to think. Thinking is more than aggregation. If you look at most of what I've described, it's aggregation and synthesis. It's not insight. So the computer will construct for you, here are 15 arguments why maybe you shouldn't run, you'd run the campus. That used to be the case, right, some years back. It'll construct that. Which of those is really going to strike resonance? Which of those is not? I don't think the computer can do. So I think all of these are tools. It's like arguing calculators are useless or spell checkers are useless. And after 10 years of fighting it, everybody said, actually, it doesn't really matter. So I think of these still as tools that make humans more productive, make humans faster, bring more things in accessibility. I actually don't believe it yet replaces thinking. Maybe it frees up the human to do more thinking.
I don't know much about this, but I have heard stuff about analog computers, and I'm wondering if you see any applications for those.
I certainly believe it's possible. I believe that if we look at certain classes of problems, analog computers absolutely could have a place. The question is, can you make them, the input and output is not yet an easily solved problem from what I can see. So same answer, by the way, for quantum computing. I actually believe it's more practical now than it was a decade ago, but input and output is still not an easy problem.
You really made an exciting pitch for the synapse chip, which is the neurons. Watson is doing lots of things. I mean, I'm using Wenmei's words and and is doing helping us think. But really, in the societal things, we need to control real systems. So, and that requires, where is the possibility of marrying Watson and synapse to control real systems? Is there some thinking along those directions?
I'll say that thinking, Ravi, is probably primitive. So marrying Watson and synapse, yes, you could imagine that we are certainly going to do that because at the least it'll give us an acceleration and capability of what Watson can do. So in that sense, synapse is an elemental architecture that's superior to implement Watson and its future. Then the second part of that, to actually help go control other systems, I think we want to do that. I don't yet think that I can turn around and look at you honestly and say that we have figured out what would be the perfect use case. Right now, all of it is a human aid as opposed to a system aid. I think a lot of that is maybe also people's fear that if you have a system that's giving you multiple hypotheses, not certain, not deterministic, you're going to help it control real machinery that does real things is kind of, I think, where we got to break through the bottleneck. Because my reaction is, the human who controls it also is actually error prone. The human who controls it is not actually deterministic.
So, carrying on from that question, Watson, synapse together, and you drew the line at insight. So, to quote a movie, Hal, is it going to be born quite yet?
I don't know, did Hal really have insight or did... So the question you're asking is one that, look, I can't give an answer to. We can all speculate. Will these systems get conscious to the point where they kind of start doing things for themselves? I mean, in these systems, if you look underneath, do they create hypotheses that no human would have conceived? Absolutely. But it's still, to be honest, in the end, right now, you can still trace back and say, look, it found two relationships, it found them in these three documents, it linked them together, is what it's doing. Is it really coming up now to write a brand new brief? Is it coming up with a new law? Is it coming up with, this will be good for society? We are far from those things.
And related to that would be a Turing test, of course.
That may be more within reach. Clearly, when I talked about this, you could see, I mean, I'm not quite saying that that's what we are after, but you could imagine that is one of the goals. I think a Turing test is much simpler than consciousness and creativity.
Actually, a lot of these questions relate to what I was going to ask, but I will ask you to go a little farther on the control aspect, and particularly your observation that it's perhaps more human fear than reality that these systems can't work as well as humans in control, particularly in cases where decisions need to be made quickly, right? And particularly where the decisions are maybe not life critical. So, you know, we all know about autopilots and the co-pilot that's the dog that will bite the human to make sure he doesn't touch the controls. Can you be a little more specific? I mean, is IBM really not going to try to use this for control because of that non-technical reason, or
No, I didn't say we wouldn't try to. I said we are not yet there. So we tend to, for controlling systems other than our own plants, we by and large tend to work with clients. If I take some examples from the world today that are very simple, but where we have worked with people, I mean, doing credit card processing is now straight-through processing. Although the systems were built by people like Visa, MasterCard, American Express, Bank of America, Citigroup, and we work with every one of them with those, and there is no human. There's no team, there's no thousands of humans who can help process. I think Visa at peak is 2.5 billion transactions an hour or something. Right. So those are systems where clearly they turn around and say, not only do we trust the system is the basis of our competitive advantage. And they make those better and better and better over time, albeit in a very narrow domain. Ditto for airline scheduling, ditto for airline reservation and pricing systems. Those are no longer done by humans, those are done by computer. I would imagine that energy could be another area where I think these could be applied. I think transportation. Look, I mean, a colleague of mine made a very simple observation that for the set of folks in the room who do any kind of performance management, you all know Little's Law, right? Or some of you know Little's Law. Little Law says, you know, kind of work in progress divided by cycle time tells you, service time gives you the cycle time. So you say, I want to reduce my cycle time. So the completely non-intuitive answer for a human workforce is reduce the work in progress. Right? And you start to say that's counter, because people love to throw more work at people. And you begin to look at those things in the context of congestion networks, roads, how do I control inner city traffic? You're not going to service at over capacity. That's not going to happen, regardless of what you want. So figure out the capacity and then figure out how to control things. I believe systems like this are going to get you there, not humans.
If I can just follow up with one question. At the beginning, you brought up energy, and you talked about these kind of huge computing systems aren't going to be used to control energy. So I want to ask you the business question, but I imagine then we can aggregate, and so then we have energy management as a service. Are these big systems going to be used for energy management as a service?
I believe that is going to be one of the possibilities. We saw some commercial reaction from that. We reached out to the Weather Channel earlier this year and asked the Weather Channel whether they'd be motivated to go to every utility company and leverage their data to help the utility companies improve their operations. And their answer actually was interesting. Yes, we would be, but you do it. Because of exactly that reason. They didn't think that they would go build a computer system for every utility, but they felt we could stand up one that actually could be a service then to every utility company on the planet. And so I'd say there is definite credibility in this thing. So we'll begin simple, and hopefully once you begin, you get more experience and keep going deeper.
You realize circuits in, silicon, germanium, arsenic, whatever. Have you looked at realizing circuits in something biological? Neurons, DNA for storage, CRISPR comes to mind, which I can't even explain, but I've heard the word.
So implementing biological artifacts in silicon, germanium, gallium arsenide, nanotubes, graphene, etc., yes. Using actual biological materials, we have not, because I'll go back to, there was a lot of experiments done in universities around DNA computing and so forth. Problem was, I still don't know how to give it a problem. It did certain problems, but those were what it was designed to do. So if you can't tell it what problem you want to solve, I don't yet know. If that gets solved, maybe. The other problem, of course, right now is sustainability. How long does it function? I can't have it do one operation and kind of die.
Maybe one more question, Jim?
Yeah, with regard to the plane crash over France and the co-pilot, the thing that occurred to me right away is why wasn't the system programmed to prevent that? It should be able to figure out that what he tried to do was not possible. It shouldn't be allowed.
So I'll give you the counter example to that one, which unfortunately, that one was Lufthansa or German wings, which is this thing. So the counter example would be the Air France one, which went down over the Atlantic, the one from Brazil going to Paris. There, actually, the system was trying to make it dive, and because the pitot tubes had gotten frozen. And so the question is, how accurate is all your input? So they always say the pilot can override the autopilot, because could be the sensor data is wrong, could be the electronics got fried, could be a chip got busted. So you say, we can get into all of the resilient, reliable, fault-tolerant aspects. They don't go away. And so if you say, well, if those are wrong, then my system is useless. And so that was the reason they always have so far allowed for pilots to override the system.
But they could force the pilot to talk to ground control and have an interaction to see if they could solve the problem, which is correct. But definitely what he tried to do was...
Well, they could, but if the pilot doesn't want to, yeah. So the whole human side of it becomes messy. But I think that until we can prove that the system cannot get faulty, you're always, right now, going to react with, I got to give the pilot eventual override, at least right now. I think that's the real concern there.
Okay, thank you, Arvind.
Illinois.